Section P.5, factoring polynomials. The objectives for this section are going to be to factor out the greatest common factor from a given polynomial, to factor by grouping, factor trinomials, and factor the difference of squares, factor perfect squares polynomials, the sum and difference of two cubes using a method called SOAP, right? Little acronym for that. And then use a general strategy and talk about how to best approach a polynomial if you want to factor it. And finally, we'll finish with factoring algebraic expressions containing negative and fractional exponents. Okay? So when we talk about factoring, basically what we're doing is we're breaking down some sort of polynomial into two different things multiplied together. So factoring a polynomial expressed as a sum of monomials means finding an equivalent expression that is a product. We're taking something that's a sum and changing it to something that is a product. Could be a product of two different things, could be a product of three, four, it doesn't matter. Okay, doesn't matter how many monomials we start with. In this case, we started with two, and we broke it down to a product of two different things. When we factor in this class, we're going to be factoring over the set of integers, meaning that the coefficients in the factors are all going to be integers. I could start with an expression like, start with an expression that looks like that, and we can kind of see that there is no integer that goes in both 2 and 3. What I don't want to do is something like that, which would then turn this into 4x plus 6. I don't want to start factoring out fractions. I only want to factor over the set of integers. Okay? So no good for those. The next point here is that polynomials that cannot be factored using integer coefficients are called irreducible over the integers, or even better, prime. Okay? We can be irreducible over many different types of numbers, not just integers. For example, this particular polynomial is irreducible over real numbers. You could factor it if you wanted to use imaginary. Again, that's something that we'll get to a little bit later. Okay, but for now, we're going to focus on just reducing it over the integers. And if we can't do it, we're going to call it irreducible or prime. And so what's my goal with all this? So my goal in factoring a polynomial is to use one or more factoring techniques, and we're going to talk about a lot, right? We had 8 little objectives there at the beginning, so we're going to talk about a lot of factoring techniques. So we're going to use one of these until the polynomial factors, except for maybe a monomial at the beginning, is prime or irreducible. So in this situation, the polynomial is going to be said to be factored completely. So that's what our goal is. Our goal is to get it down until pretty much we can't do anything else. Let's take a look at what we mean here. Okay. First, we're going to talk about the easiest way to factor, which is finding a common factor. So in any factoring problem, the first step is to look for something called the greatest common factor. Okay? And the greatest common factor, most commonly abbreviated as GCF, is an expression of the highest degree that divides each term of the polynomial. Right? These can be numbers. These could also be variables. The distributive property in the reverse direction shows that we have an a in common here, right? And I can factor that out. This is the largest degree, a to the first power, that is in common with both terms. So I can factor it out. I can use the distributive property in reverse to factor out the greatest common factor. Let's try some problems. Okay? So if I want to factor this expression, I have to ask myself, what is the largest number that divides into both 18x to the third and 27x squared? And it is 9. Also, the highest degree of the variable. Okay? So x squared divides into both. And now I have to ask what is left over. So if I divide 18x to the third by 9x squared, I would get 2x. Divide 27x squared, I would get 3. Okay? Then I ask myself, is this irreducible? Yeah, there is no other integer that I can take out of 2x plus 3. And that's a monomial. I don't want to do this. I don't want to break it up into other prime factors. That would look crazy and a bit weird and be lots of extra work. Okay, so we're not going to do that. We're going to stop right there with that expression. Okay, and we're going to say that that is factored completely. If I look at this expression right here, now it's not a number that they have in common, but it is an expression, right? They both the first term right there and the second term have x plus 3 in common. So when I factor these, that's what I'm going to factor out. I'm going to factor out the x plus 3. And what's left over in this first term is x squared. And in the second term, we have a 5 left over. So in this case, my common factor, my greatest common factor, is a binomial instead of something else. Okay. The next technique we're going to look at is factoring by grouping. So some polynomials have only a greatest common factor of 1. However, by suitable grouping of the terms, it still might be possible to factor them. This process is called factoring by grouping. And if we look at this expression right here, I have an x to the third, an x squared, an x, and a 12. None of them have a variable in common, and none of them have any numbers in common. There's nothing that I can factor out of all of them. But if we group the terms the right way with these two and these two, I can make them have a common factor. Okay? So in between these two terms, they have an x squared in common, which leaves me with x plus 4. Plus, these two have a 3 in common, which leaves me with x plus 4 again. And now because they both have a common binomial factor, I can factor that out. And what's left over, just like the previous example, x squared plus 3. Okay? And so that's how factoring by grouping works. We are going to factor something out of the first two terms and the second two terms, and if that thing that's left over is the same, I can use the distributive property backwards to group x squared and 3 together into one factor and x plus 4 together as well. This technique is most commonly used when you have x to the third, x squared, x, and a constant term. Okay? Now, it doesn't really even matter if I were to look at this in another way, x third plus 3x plus 4x squared plus 12, which I would never write it that way because it's not in standard form. But watch what happens. The first two terms right here have an x in common. Gives me x squared plus 3. These second two terms only have a 4 in common, which leaves me with x squared plus 3. These two are now my common binomial factor. I can factor it out to give me x squared plus 3 times x plus 4. So it doesn't matter which way I group the expression, I should end up with the same factored form. Okay? But we are always going to put it into standard form like it is in the first one, so that is a good habit to get into there. So, factoring trinomials is probably one of the more important skills that you should have gotten from Algebra 2. Okay, so to factor the trinomial in the form of ax squared plus bx plus c, a little trial and error might be necessary. And this is usually the strategy that I would use to factor uh, a quadratic trinomial, right? 3 terms, x to the squared power. Okay? So assume for the moment that there's no greatest common factor. And if there was, the very first thing you should do is factor it out. It helps by making all the other numbers smaller and easier to work with, okay? So if there is a greatest common factor, the first step should be factor out that greatest common factor and then look at what's left. If we remember how we FOIL things, okay, right? If we have an expression, let's just say x plus 2 times x plus 3, if we were to FOIL these two things together, the first terms would multiply together, then the outside, then the inside, then the last ones. And you see that the first term gives me that expression. The last two numbers give me this piece right here. And these two are going to add together because they're like terms. Okay? So going back for a second, find the first two terms whose product is this thing right there. So I want to first find, I want to first find two numbers that multiply together to give me that there. Then I want to find two numbers that multiply together to give me that. If they're prime, if they're 1, it's very simple. If they're prime, it's easier. There's only one choice. When this gets a little more difficult is when there's a lot of choices, when there's multiple choices. Now the tricky part, and where the trial and error comes, is you have to make the inside pair and the outside pair multiply together, and when you add them, you get the middle term. Just like when we did here, when we look at these two middle terms, my final expression here would be x squared plus 5x plus 6. That doesn't look like a 6. Plus 6. Okay? So just looking at the 5x, it's tough to see where that came from without looking at the 3x plus the 2x. It's easy to see where the x squared comes from, x times x, and it's easy to see where the 6 comes from, something times something to give you a 6. Okay? So with that in mind, okay, we're going to go through these steps, and we're going to try to make my factoring expression actually work. Okay? If nothing does work, if no combination exists, the polynomial is prime. Okay? So let's try it. Okay? So when we factor, it's a little bit easy to factor when you have a trinomial whose leading coefficient is a 1. Okay? So first, we're going to find two things that multiply to x squared. Well, we're not going to do weird stuff like that, because x to the negative 1 times x to the third is x squared. We're not doing that, okay? We're going to keep it nice and simple, and we're going to just keep whole number exponents. X times x is x squared. Okay? Now here's the tricky part. There are 4 sets of numbers that multiply together to give you 8. 1 and 8, 2, 4. There's still 2 more, because don't forget about negative 1 and negative 8, and negative 2 and negative 4. So out of these 4 possible pairs of numbers that multiply together and give me a positive 8, we want to find the one whose adds up to 6. Okay, and we can clearly see that it's going to be 2 and 4. So that's x plus 2, x plus 4. Okay. The way I like to read this trinomial, when there's a 1 in here, like again I said, this is a little bit easier, is going to be the factors of 8 that add to 6. Okay. If this was a negative 6, it would be the factors of 8 that add to negative 6. Okay. let's take a look at this one right here. The factors of 42 that add to negative 13. So when I do this, I'm going to make my two sets of factors. I'm going to start with an x. Okay, factors of 42 that add to 13 are going to be 7 and 6. Negative 7 and negative 6. Negative 7 times negative 6 is positive 42. Negative 7 plus negative 6 is negative 13. And when I want to check this, I can FOIL it together. Plus 42. And I can see that when I combine the middle terms, I do get my original expression, which is good. That's what you want. When there's a negative in the back and a leading coefficient of 1, the only difference is now the only two numbers that can multiply together to give you a negative 18 is going to be one positive number and one negative number. Okay, so again, my first two terms are going to be x. Okay, and now the factors of 18 are 1 and 18, 2 and 9, 3 and 6. Okay, but one of them has to be positive and one of them has to be negative. So those three would be positive or negative, and these three positive. Okay, and now you ask yourself, which pair of these add together and give me a positive 3? And it's going to be that pair. So see x minus 3, x plus 6. Okay. And the way I like to read this one is the factors of 18 that subtract and give me 3. Right? Because one side's going to be positive, one side's going to be negative. So 6 minus 3 gives you 3. All right. Now the trial and error comes from thinking about all these possible different combinations. When we have an expression that is basically pretty straightforward like this one, we don't really have to go too crazy trying to think of all the different combinations. Where it gets a little bit more difficult is when we have an equation like this. Okay, so what you want to think of for this expression is if this sign is positive, the signs are going to be the same. If it's negative like it is here, the signs are going to be different. Like back here, that sign was the same, or sorry, this sign was a positive. These two were the same. They were both positive, like the first sign. Okay? This is a negative. They're both opposite. The bigger number is positive because I want my answer to be, we want my middle term to be positive. Let's look at two methods for solving or for factoring a trinomial whose leading coefficient is not a 1. Okay? So I'm going to have two possible choices here. I could have an expression like this, 8x and x, or I can have an expression like this with a 4x and a 2x. Because both of these, 8x times x is 8x squared, 4x times 2x is 8x squared. So both of these are possible. Okay? So when we're guessing and when we're checking, right, it's a good idea to try to think about both. And the way I like to do this is I like to list the factors of 8, 1 and 8, 2 and 4, and I like to list the factors of 3. Luckily, there's only 2 there. Okay. Now what I do when I create my parentheses is I sort of think about where these different things can go. So let's try the 8x and the x. Okay. I could put a 1 and a 3. Okay. And then when I multiply the outside pair and the inside pair, I get a 24x on the outside and an x in the inside. I want the answer to subtract. One's going to be positive, one's going to be negative, to 10. 24x and x do not subtract to 10. Okay, so that's not going to work. I could also try it this way. Okay, that's a 3x. That is an 8x. Well, that's close. When I subtract them, or it's not really close, when I subtract them, I'm going to get either 5 or negative 5, depending on which one's positive, which one's negative, so that doesn't work either. Okay? So I know that neither one of those combinations with 8x and x worked. So I can get rid of these two, and I've successfully eliminated it as a choice. So my next option is going to be 2x and 4x. 2x times 1 is 2x. 3 times 4 is 12. And guess what? 2x minus 12x is going to give me negative 10x. So this is right. This is what I want. Now I just have to decide on the signs. Okay? I want the 10 to be negative, which means I make the bigger pair negative, the 12x. Okay? That's sort of the guess and check method. That's the method I actually prefer. Okay? Before we're done here, I'm going to show you one more method. Okay? The grouping method has its pros and its cons. Okay? It's good if the numbers are small, like they are in this problem. The biggest issue is that the first step of the grouping method is to multiply the first and the last number together. So if these numbers were bigger, it then becomes a matter of finding the factors of a very large number, which can get kind of difficult. Okay, so with the grouping method, I'm going to take the 8 and the 3, and I'm going to multiply it together to give me 24. I then find all the factors of 24. 1 and 24, 2 and 12, 3 and 8, 4 and 6, and that's it. That's about 6. Okay. Then I want a pair of these that subtract to give me negative 10. Okay, so that's going to be a positive 2 and a negative 12. And we can be technical and say that they have to multiply together to give you negative 24, so one's going to be positive, one's going to be negative. That's fine. But what I'm going to do is I'm going to take this original equation and I'm going to rewrite it. But what I'm going to wind up doing here is I'm not going to write the 10x the way it is. I'm going to take that away and I'm going to split it up into plus 2x minus 12x. Still 10x. I didn't change the problem at all. But what this allows me to do now is to group the first two. They have a 2x in common. And what's left over is 4x plus 1. And now these two have a minus 3 in common. And so what's left over is again a 4x plus 1. Notice these two are the same. So we can factor this by grouping, or sorry, we can factor the 4x plus 1 out. And we're left with the same expression that I had up here. Okay. Let's not do that problem down there. Let's try one more. Okay. And my factoring problem is 6x squared plus 19x minus 7. Okay, so I think about my factors of 6. 1 and 6, 2 and 3. My factors of 7 are 1 and 7. Okay, and I'm going to use the guess and check method here. And basically, what I do is I think about, okay, the 1 times the 1, the 6 times the 7 has to subtract to 19. Well, the 6 times the 7 is 42. If I subtract 1, that's not going to work. 6 and 7, that's going to give me 1. So this one's out. So I know my answer is going to be 2x and 3x. And now I just need to figure out how I can put these two together. And I want 21 minus 2. And I want my middle term to be positive. And remember what I'm looking at here. I'm looking at the inside pair times the outside pair for my FOIL. Okay? And if you're not sure, FOIL it out. 2x times 3x would be 6x squared. Outside would be minus 2x. Inside plus 21x. And last would be minus 7, which, when I combine these two, gives me my 19.